All right, so what we want to do today is talk about how you would use the circle method to attack certain problems. So just how you would set things up. And then after that, I'm going to switch to class presentations, and I'll turn off the camera for that and just discuss a little bit of what you read from some of the papers. So circle method. So the goal is to see how flexible the circle method is. So step one is deciding what the problem is. Step two is figuring out the formulation. Step three is doing the calculations on the major arc. And step four is doing the calculations on the minor arc. The 4 steps get increasingly difficult as you go down. And in a lot of the problems, we can't even do the minor arc calculation. Frequently, we can do the major arc calculation, but in some sense, this is a little bit of a misnomer, if that's the right word, because we don't necessarily know what the minor arcs should be, so we're not quite sure exactly what the size of the major arcs should be. The hope is that we have some rough idea of approximately how big the major arc should be and have a good sense of what the answer is. So does anybody have a favorite problem that they would like to see the circle method attack? We have Waring, we have twin primes, we have Sophie-Germain primes, we have Fermat's last theorem. Twin primes. All right, now, when we were trying to do Goldbach, the question was, are there, given an integer n, can we write it as the sum of 3 primes, as the sum of 2 primes? If we did something exactly like that for the twin primes, it would be boring. Are there 2 primes that differ by 2? This is not that challenging. I'm not going to bother going through the setup of the proof. I will just, there was a beautiful proof years ago where a mathematician went to the board and didn't say any words. He just wrote something down. So in homage to that, I will just write something down. All right. The existence of twin primes is not difficult. This is not one of the times when we prove twin primes exist by showing that there exist infinitely many twin primes and therefore there exists a pair. Right? We don't need to go to that level of detail here. We can just write it down. So this is very different in flavor from the Goldbach problem, where if we want to show that a representation exists, we had to show that there were many representations and went from many representations to one. Here we already know that there is a twin prime. So we need to write it a little bit differently. So now the question is, how many up to x? And if you think about this, this is one of the most basic questions you can ask in mathematics. If I have some quantity, how many do I have? The first is existence. Is it worth counting this? One of my advisors, Henrik Evanits, I'm not sure if he was the one who coined this, has a really nice joke about the Riemann hypothesis. That people are spending their lives, when they're investigating this is an aside, here's 0, here's 1, here's 1/2. We know that there are no zeros on the line real part of s equals 1. We have results like this that say there's some strip whose thickness is decreasing as we go down, such that there are no zeros in this strip. This gives us an estimate on the prime number theorem. But there could be non-trivial zeros of the Riemann zeta function off the half line. People have actually found bounds. And they'll say, if you choose some sigma over here, how many zeros could you have in this window up to height t? And we actually have some decent estimates about how many zeros there are with real part at least sigma up to height t. And my advisor has phrased this as people are trying to get better and better estimates for the cardinality of the empty set. I can show the empty set has at most this many elements. I can show the empty set has at most this many elements. So at the end of the day, of course, we expect that there is nothing here and that we're just trying to get better and better estimates of the size of the empty set. So after you prove something exists, which we have not proved, fortunately, for the non-trivial zeros, the next question to ask is how many? Well, that density set that I just erased is in some sense similar in spirit. How many zeros do we have off the critical line up to a certain point? How many? It's an estimate, it's an upper bound. And it turns out the fewer of them there are, the more we can do. So now for twin primes, we want to know how many up to x. So we want to solve or count all p less than or equal to x minus 2 such that p and p plus 2 are prime. When you're doing something like this, it could be a little bit annoying. Are we counting all primes up to x, all primes up to x minus 2? Doesn't really matter, right? We're talking about at most one more pair, Notation can be annoying. Okay to do p less than x minus 2 or p less than or equal to x. There's really no difference between those two. So now we want to do the circle method. So we want to have some kind of counting function. So again, our function is going to be fn of x is going to be the sum p less than or equal to n of log p e to the 2 pi I px. And so often when we count, we want to count how many primes up to some number x. When we write a function like this, we typically use the letter n because we want x to represent something in 0, 1. And so now what we would look at is we would look at fn of x times fn of negative x times e to the negative 2 pi I 2x dx. Integrate from 0 to 1. And if you think about that, what this is going to do is this is going to give us a sum p1 less than or equal to n of log p1 e to the 2 pi I p1 of x. The next one will be a sum of p2 less than or equal to n log of p2 e to the 2 pi I p2 of x. And then the last one is going to be e to the negative 2 pi I 2x dx. Integrate from 0 to 1. All right. We've done this numerous times all semester. What do we do here? Switch, right? We've got integrals and sums. This is the sum p1 less than or equal to n, the sum p2 less than or equal to n. And now we have the integral from 0 to 1. Actually, I'll put the logs outside. The log of p1, the log of p2, the integral from 0 to 1 of e to the 2 pi I. Oh, oops, this is a mistake here. What's the mistake over here? It should be minus because I'm evaluating it at negative x. So I'm going to get p1 minus p2 minus 2 times x dx. Well, when I look at this integral, the only time this integral is 0 is if p1 minus p2 minus 2 equals 0, which means p1 equals p. 2. I'm sorry?
Only time it's 1?
I'm sorry, the only time it's 1 is if p1 minus p2 minus 2 equals 0. And it's 0 otherwise. So it's 1 if p1 minus p2 minus 2 equals 0, which implies that p1 equals p2 plus 2, 0 otherwise. And so the way we're doing it over here, we actually have p1 is coming in as our larger prime. Does it make a difference? No. And so this integral will be 1 every time we have a twin prime pair. And now we are left with the weighted sum. And so this now gives us the sum over p such that p and p plus 2 are prime, log of p log of p plus 2. And that's going to give us a weighted count of how many twin prime pairs there are up to n. Can I just write p here instead of p plus 2? Sure. How harmful is it to go from the log of p plus 2 to the log of p? Let's just quickly look at that estimation. So if we look at the log of p plus 2, this is the log of p times 1 plus 2 over p. The log of a product is the sum of the logs. This is the log of p plus the log of 1 plus 2 over p. This is the log of p plus big O of 1 over p. Because when I expand the logarithm, p is going to be large. If p is not large, well, there's only finitely many p that aren't that large. And in the limit, they're not going to really matter. I want to know how things are going off to infinity. A couple of primes here and there won't matter. So when I look at the contribution of the log of p plus 2, the difference between it and the log of p is so small, it doesn't really matter. What will I be left with? I'll be left with the sum of log p over p. Now the sum of log p over p is not completely negligible. So the sum over p, a twin prime, of log p plus 2, this is going to be the sum of p twin log p squared plus an error term of psi sum p is twin log p over p. This is significantly smaller than this. Right? So the question is, what can you say about that sum? So it turns out the sum of the reciprocals of the primes diverge. If this was over all primes, this would diverge. But it wouldn't be diverging by a huge amount. It would be very controllable. So we could even estimate this by extending this up to a sum of all primes. But we want to make sure it's still much smaller than this. It turns out the sum of the reciprocals of the twin primes converge. So Brunn proved this, and it was a very disappointing result. Because people were trying to prove that there are infinitely many twin primes. If the sum of the reciprocals diverge, the only way that can diverge is if there are infinitely many. Unfortunately, because the sum converges, you have no useful information. Have I talked about Brunn in this class? No. Okay. How many of you have taken a computer science course? How many of you have heard of the pentium bug? This is one of the greatest applications of pure mathematics. So Intel had launched a campaign saying the most important part of the computer is the processor. And they used to call things the 286, the 386, the 486 for their chips. Then they called the new one the pentium chip. I've been trying to find a pentium chip to buy and just have on a keychain. Turns out that the Pentium chip had a small mistake in it, and it would occasionally make mistakes when doing divisions. Not often. It would take like 1 billion divisions to really see a mistake, and it would be like the 9th decimal place. Intel knew about this, but they figured, who the hell is going to be doing 1 billion consecutive divisions where they need 9 digits accuracy? And so Intel didn't say anything about it. And so Nicely was looking at the sum of the reciprocals of the twin primes. He knew it converged. He was trying to compute what it converged to. And on his new Pentium, he wasn't getting the same result for the first few digits he got on his 486. And so eventually this came out that there was a problem with the Pentium chip. And so it was a wonderful story. It's one of the few academic materials that my wife, who's a professor of marketing, and I both teach, although from slightly different perspectives. The competitors to Intel agreed with Intel that the most important part of your computer is the processor, and ours can divide. Intel had an extremely costly recall where they said anybody who is afraid that they will be affected by the defect can send their Pentium chip back to us and we will send you a new chip. And so you have all these people who are getting new chips who don't really need it. But this was discovered by just trying to compute a number theoretic constant, the sum of the reciprocals of the twin primes. Anyways, the main thing here is the main term is going to be the sum of log p squared. We would then use some kind of partial summation to pass from this to counting how many twin primes there are. This is giving us the weighted number of twin primes. Or equivalently, if you want just a quick rough heuristic, I'll end with a quick rough heuristic as to what this is. Any questions first on how we set up the calculation? Okay. So the belief is when you then do the circle method and do the calculation, the main term for twin primes so the twin prime conjecture, there exists a C, and we actually have a formula for it, such that the number of twin primes less than x, we'll call it C2, is approximately C2 x over log squared of x. So we actually expect that there's a lot of twin primes. And so if you're doing that, if you look at the sum, p twin p less than or equal to n of log of p squared. If you want to try to get a sense of the size, this is clearly going to be less than or equal to the log of n squared times the sum of p twin p less than or equal to n of 1, which is log of n squared times pi 2 of n. That bound is no problem. What about the other direction? What if I wanted to get a lower bound for this? What would be a good lower bound? If I just want to care about the right growth rate, x over log squared x, n over log squared of n, what would be a really good lower bound?
Sum over all the primes of log prime.
Okay, sum over all the primes.
Of log p all the way. I don't know.
You have to tell me what range to sum over.
From 1 to n.
Well, if I'm summing from 1 to n, that's all the primes. I want to restrict. Where should I start counting?
5.
Well, 5 is the same as starting at 1. You've got to give me some starting point that's a function of n. Right? What would be a good starting point? Okay, n over 2. Now the problem with n over 2 is it's essentially the same size as n. That could be very hard. I'm sorry? One possibility is log of n go really far down. Log of n might be too far down. Root n. So the difference between all of these is if you look at the log of p, if you take p about log of n, that implies the log of p is about log n. If you take p of size n to the a, that applies log p is about a log n. So once I'm a power of n, all these log squareds are essentially the same up to a constant. If I go all the way down to log of n, they actually differ in size. And so, again, I will lose out in the constant, but in terms of just the growth rate, I'll get the right growth rate. So in questions like this, you can always do things in some generality, and we can say that this would be greater than or equal to the sum of n to the a less than or equal to p less than or equal to n. P is a twin. Log of p squared. And now I can replace this with a log n squared, the sum n to the a less than or equal to p less than or equal to n. P is a twin of 1. And so now this is going to count how many primes I have twin primes I have from n to the a to n. If we expect something of size, x over log squared of x, if I have any value of a that's less than 1, there's so few twin primes up to n to the a relative to from n to the a to n. So think of a as 3/4. I would expect to have roughly n to the 3/4 over log squared n to the 3/4. Can you give me a trivial estimate for how many twin primes there are up to n to the 3/4? Trivial estimate. Do not think much. How many twin primes can there be at most n to the 3/4? N to the 3/4. Right? Worst case scenario. Every integer is a twin prime. Amazing. Right? Be crude, be lazy, be as lazy as long as you can. This is so much smaller than the expected main term that if we wrote this over here now as a log n squared pi 2 of n minus n to the 3/4, then we'd be fine. And we can use that to get a really good estimate for pi 2 of n. So now we would just need to know essentially what is the sum. And now notice we essentially have the same thing with log squareds. And now we can figure things out. Okay. As long as we're here, let's just do one more thing on the twin primes. Let's do a heuristic as to why it should be x over log squared. So we'll do heuristic for twin primes. Sometimes these calculations can be made rigorous, but if not, they're still very useful for getting a sense of what the game is, what the results should be. What is the probability n less than or equal to x, well, let's say t is prime? What would you guess the probability n up to less than or equal to t is prime? Well, maybe let's just do probability n is prime. If you had to guess, what would you say the probability that n is prime?
For 1 over pi n.
I'm sorry?
1 over pi n.
Not 1 over pi of n. 1 over log n. So the reason is the density of primes is about 1 over log x up to x. The spacings between primes around x is about log x. So about every log x numbers, you'll get a prime. So if x equals n, it's about every log n. So number of primes less than or equal to n is pi of n, which is about n over log n. Average gap is approximately log n, because the average gap times the number of primes must equal the distance. Average gap times number of primes equals interval. And so here we would have log n times n over log n would be the size of the interval. So expect 1 out of every log n integers to be prime. Okay? So as a quick heuristic, the probability a randomly chosen number is prime is about log n, is about 1 over log n. Do you buy this completely?
Well, it's really a little bit less.
Why a little bit less?
Because they're concentrated towards the beginning of the
So maybe it's a little bit less, but then of course then we need to know, well, what's the next order term in the prime number theorem? Maybe that bounces things up a little bit. So not a bad thing to worry about. Maybe we're off by a little bit, but roughly it should be around log of n. Now if I choose an even number, what's the probability it's prime? 0. So right now I'm assuming I have no information at all about what kind of number I'm choosing. I'm just choosing some number. I think I'm finally getting the hang of how to walk with a swivel. All right. What is the probability n plus 2 is prime? Yeah, let's not really worry. Let's not really worry about the plus 2. And we've just already talked about how we don't need to worry about that. What is the probability n and n plus 2 is prime? Oh, that's probably telling you to read Borevich, Shafarevich, or something like that. So why is this step problematic?
We assume the primes are independently distributed.
Right. This is assuming independence. If I know that n is prime, that gives you some information about n plus 2. Do you think n plus 2 is more or less likely to be prime?
Less.
Less. Why?
Because if it were more likely to be prime, then we could probably prove that the sum of them diverge.
No. Not a bad thought, but no. What does it mean for a number to be prime?
Only by itself in 1.
So if I try to look at my number n, let's say n is big, its remainder when I divide by 3 is not 0. Its remainder when I divide by 5 is not 0. Its remainder when I divide by 7 is not 0.
It's because if n is not prime, then n plus 2 also... No, that's what that means.
Well, wouldn't it be a higher chance it's prime? Because like half the time n will be even, and then n plus 2 will also not be prime.
Well, but if n is even, game's over.
Yeah, okay.
But I'm saying, if n is prime, n cannot have a remainder of 0 modulo any small prime. So now you know that if I look at n plus 2, well, n did not have a remainder of 0 when I divided by 3. So this means n was either 1 or 2 mod 3. Oh, well, if it's 1 mod 3, n plus 2 is going to be divisible by 3. So, did I say it the wrong way? Okay. Right, so, if n is 1 mod 3, that implies n plus 2 is a multiple of 3. If n is 2 mod 3, that implies n plus 2 is not a multiple of 3. So what we've just seen is that 50% of the time, if n is prime, n plus 2 can't be prime. And what you can do is you can actually incorporate all of this for the various things and get better estimates and get a better value of the constant. So I'm not going to do that. You can fix this a little bit. So what we could then do is estimate pi 2 of x, which will be the sum n less than or equal to x of 1 over log of n squared. How would you estimate that sum? For each n, this is the probability I get a prime. I'll sum them all together. How would I estimate that sum? So this is another technique that can go into the book for the class. Whenever you see a sum, what do you want to replace the sum with? An integral. So this should be approximately the integral, t goes from, say, 2 to x of 1 over log of t squared dt. Notice that pi of x, counting how many primes are at most x, would be approximately the sum n less than or equal to x 1 over log of n, which would be like the integral from 2 to x of 1 over log of t dt. And as a nice exercise, show that this is 1 over log of x smaller than this. And then the question becomes, how do you get the main term? How do you get that constant? I'll put up a really nice article by one of my mathematical brothers of how to try to elementarily fix this argument and actually get the twin prime constant, to get this number C2. So there's a lot of really good stuff going on in this problem, from heuristics to try to figure out what the answer should be, to how you would estimate the size of these integrals and sums, to why you would care about this, keeping Intel honest. Lots of nice stuff for this. Yes?
Is there anything that makes the minor arc calculation particularly hard?
Yes. You just don't have, you only have two things. You have fn squared. And so as we saw last time, we want to pull out a maximum value of fn over the minor arcs. That leaves us with the L1 norm. The L1 norm is comparable to the L2 norm. The more things we have, the easier it is.
So do you get similar results for the gaps of size 4
Yep.
and size 6?
Yep, and in fact, the whole theory follows analogously. And you can just say, I want to have a gap of size 2m, and you can calculate this. And these are called the Hardy-Littlewood constants.
And for triple gaps, where it's
Yep.
gap of 6, gap of 6.
Right. So I think it's called constellations. For extra credit, can anybody give me the Star Trek episode with the ship called the Constellation, and what was its number? It's the episode with the giant shofar. So let's say you want P plus A1, P plus A2, P p plus ak. I believe it was called the Doomsday Machine, and I believe the number was the NCC 1017, because I think they just took the 1701 from the Enterprise because the budgets were a little bit tight and just rearranged the numbers. They didn't have much money when they were making Star Trek. So I think they used the 1701 and just rearranged the numbers a little bit to save money. I'll have to check that. I'm sorry? You know, if you've got the stuff that you can quickly move it around. Let's say we want all of these to be prime. What can you tell me about the A's? Even unless I'm in the stupid case that this one is 2, in which case I'm not going to have infinitely many. Okay, so let's say I want something like this. Can we set up a circle method calculation for this? So again, we'd have fn of x would be the sum p less than equal to n of log p e to the 2 pi I px. And now we would integrate from 0 to 1 fn of x, so that would give me my p. Now so if I want to take the sum of all of them, let's see, how do I want to do this? So the second one has to be the first one plus a1. The next one has to be the first one plus a1 plus a2. And so the question is, you know, are there choices so that you can get the constellation? I want to make sure I leave time for you to do it. So I will leave this as an exercise. You know, to set it up so that you can do the twin prime constellation. Yes?
Don't we have to be a bit careful when choosing the A's because it's trivial?
Well, some of the A's will not lead to infinitely many. So if you try to do p plus 2, p plus 4, good luck. You know, you'll find 3, 5, 7, and that's it.
They all have to be divisible by the first k primes.
What's going to happen is you're going to have parity issues exactly as before. When you try to calculate your major arcs, there's going to be this multiplicative term in front that is going to depend on properties of the A's. And if you choose the A's poorly, it's not going to work. So I'll do one last one. I'll set up Fermat, and I'll switch to presentations. So let's try to do Fermat's last theorem. Okay, let's see. No, unfortunately, the blackboard's not quite wide enough to do this. So I actually had the fortune of taking classes and teaching classes with Professor Andrew Wiles. And because of that, I occasionally get submissions of Fermat's last theorem proofs because people have found our names on the web together. I did not say correct submissions, just submission. Okay, so solve x to the n plus y to the n equals z to the n, x, y, z does not equal 0, n greater than or equal to 3 is an integer. The first thing we want to do is we want to find a function. What should our function be? So before we were doing the sum of log p e to the 2 pi I px. We were putting in log p weights because we have learned primes to be discriminated. We have learned do not count all primes equally. Over here, are we studying things over primes? No, we must not discriminate here. We want to treat all the integers the same. And so we will sum over all n less than or equal to n of e to the what? 2 pi I. Actually, n is a bad notation here. Let's do k. What should we sum? Bless you. E to the 2 pi I kn. K to the n times x. And now if we look at the integral from 0 to 1 of fn of x squared fn of negative x dx, what does this equal? It will be the integral from 0 to 1, the sum of k1, k2, k3 less than or equal to n, e to the 2 pi I k1 to the n plus k2 to the n minus k3 to the n x dx. All right? All you have to do is, okay, exercise, okay? This one is a little bit harder than the first, okay? And in fact, the way we attack Fermat's last theorem is not through the circle method. And so this goes back to a question earlier, do we have any chance of this working? The problem is we don't really have enough degrees of freedom here in terms of how the estimation is going to go. Now things are a little bit nicer that we're having sums over integers and not over primes, but here is a way to set things up. Just because you can set up a problem does not mean you have made progress. But what do you think we might be able to prove? So here maybe showing x to the n plus y to the n equals e, then maybe that's too hard. What might be more possible, might be more amenable?
Should there something finitely many cases of answer?
I think finitely many is not the way to go here. We're trying to write an nth power as a sum of two nth powers. What if we had 3 nth powers, 4 nth, or what if we had s of n nth powers? If we add more terms, you add enough terms and we expect to have a solution. Okay, so I hope this gives some sense of how you would use the circle method to set up problems.